In this video, I talk about the solution of systems of linear equations. Please open the example script example underscore linsolve, and let's put a breakpoint in line 2. We can now start the execution. We stop in line 2. We set the random number generator to its default generator and to the default seed. Let's clear the workspace just to be sure, and let's generate a random matrix A of integers. So this call to the function rand will produce a matrix of size 4 by 4 with integer random numbers between 1 and 7. If I subtract 4, the range is between -3 and +3. Let's check that A has full rank. Yes, it has. This is the true solution to the system, and B is the right-hand side. So the system of equation reads A times X equals B. The simplest way to get a solution is with left division. So X1 is A backslash B. And let's check how good the solution is by comparing A times X1 with B. And the difference is of the order of 10 to the minus 14. This is the usual order for rounding errors in a well-conditioned situation. We can do the same with linsolve. This is actually the same algorithm as the left division, but it returns also a quantity R2 along with a solution X2, and R2 is the inverse condition number. So if R2 is 0, then the problem is ill-conditioned and the solution cannot be trusted. Let's again make the cross-check, and you see that the difference between A times X2 and B is the same as before, which means that the solutions X1 and X2 are absolutely identical. So linsolve uses exactly the same method as left division. We can also solve the system with matrix inversion, although this is not recommended, but it gives in this case a solution X3, which is now slightly different from the previous solutions. You see that the difference between A times X3 and B is now slightly different from before. And if we, for instance, look at X1 minus X3, we see again differences of the order below 10 to the minus 14. Systems of this size, this small size, can also be solved symbolically with linsolve. This means that we now pass symbolic arguments to the function linsolve. The function sim converts the numerical matrix A to a symbolic matrix, which now contains not numerical but symbolic constants, and the same can be done with the right-hand side. B is now a symbolic vector of size 4 by 1, and it contains now symbolic constants. Now linsolve can be called with symbolic arguments, and of course the result will again be symbolic variables. So if you look at X4, these are now symbolic constants, and R4 is also a symbolic constant. It's exactly equal to 27 over 550. If you now compare A times X4 with B, we see that the solution x4 is exact. If the matrix A is quadratic and a full rank, then we know that we have exactly one solution. Now let's look at the rectangular system of maximal rank. In this case, we know that there are an infinite number of solutions. So let's now start with a different matrix A, which is of size 3 by 5 and contains integers in the range from -1 to 2. Let's check the rank of A. The rank of A cannot be larger than 3, and it is equal to 3, so it is indeed a rectangular system of maximal rank. Let's again define a solution, arbitrary vector x, and let's compute the right-hand side. Now let's try to solve this system with left division. We get this solution. We can actually convert this to, wrong window. We can convert this to rational numbers by using the function rats. And we see these are indeed rational numbers. And if we now compare the left-hand side with the right-hand side, so 8 times x1 minus b, we get rounding errors of the order of 10 to the minus 15 to 10 to the minus 14. But of course, we get only a single solution. Now, if we do the same with linsolve, we get the same solution again. Not surprising, it's the same algorithm. We can try to solve this symbolically with linsolve. And now we get a warning. Solution is not unique because the system is rank deficient, which means there are an infinite number of solutions, but the solution we get is a correct one. 8 times x3 minus b is exactly 0. So we get a single symbolic solution, which, by the way, is different from the ones before. If we look at the solution x2, which was obtained numerically, we get this solution. And if we use linsolve with symbolic input arguments, we get this solution, which is a different one, but both are valid solutions of the systems. How do we get all solutions in a symbolic way? For this, we have to compute a basis of the null space of A, which is a basis of the subspace of all vectors which give 0 if left multiplied by A. Let me show you that. So capital N is now a matrix. It's 2 column vectors, and each of these 2 column vectors gives 0 if left multiplied by the matrix A. Let me demonstrate that. We have a null space of dimension 2, so small n is the dimension of the null space. So the first column of n, capital N, is this vector. Now we multiply this vector from the left with the matrix A, and this should give 0. Yes, it does. So A times this column vector is 0, and the same is true for the second basis vector of the null space. This is also 0. So the vectors in the matrix capital N span the null space. Now we try to get all solutions. Now the general solution of the linear system is one particular solution, which we take to be x3. And then we add an arbitrary multiple of the vectors in the null space. So we loop over the dimension, we loop over the vectors in the null space. The loop runs from 1 to the dimension small n. Then we generate a symbolic variable called t1. This is the first parameter in the general expression of the solution, and then we add the multiple of this parameter t1 with the corresponding column in the null space. So x all is now the original vector x3 plus t1 times the first column of the null space n. And we do the same again for the second vector, the second basis vector in the null space. We generate a symbolic variable t2, and we add to the previous vector x all t2 times the second column of the null space. So x all now has this form. It's a particular solution plus t1 times the first basis vector plus t2 times the second basis vector. Here you see the power of the command or the function eval, which allows you to generate variables during execution. Symbolic variables in this case. Now we check whether this is really a solution. We multiply by the left, from the left with A and subtract B, and this should be exactly 0, which is indeed the case. If we now substitute some arbitrary numbers for t1 and t2, we get again a particular solution. Let's call it xp. So I substitute 1 for t1 and 2 for t2, and we get a particular solution, which is this one. And let's check. Again, we get exactly 0. So in this way, we get all solutions of this linear system, rectangular system of full rank. The solutions form a subspace, an affine subspace of dimension 2. Now let's look at a quadratic but ranked efficient system. Again, I generate a random matrix of integers. The size is 3 by 4. And now I add a fourth row, which is a linear combination of the first and the second row. So this system is of size 4, but has only rank 3. So it's a ranked efficient system, which again has, of course, an infinite number of solutions or no solution at all. So let's define the solution x, which is just the vector 1, 2, 3, 4. Let's compute again the right-hand side of the system. Now let's try to solve with left division. This gives a warning that the matrix is singular, which is of course true, it's rank 3, and it returns not a number as the solution vector. If we now make the check, we get of course again not a number. So it's clear that this is not a valid solution. Now let's try with linsolve. And this again returns a solution which contains only not a number, and R2 is now 0, which means that the system is rank deficient, ill-conditioned. We cannot trust this solution. So in this case, it's probably better to use linsolve because we get back the inverse condition number R2, and this tells us it's 0. It tells us that we do not have a valid solution. Now, how can we obtain a valid solution numerically in this case? We have to convert the system to the so-called reduced row echelon form, which is achieved by the function ref for reduced row echelon form. We create a matrix AB, which is just the concatenation of A and B. So B is put next to A. Let's have a look. So we have the matrix A in the first 4 columns of AB and the vector B, the right-hand side, in the last column of AB. And now we invoke the function ref and we obtain the following. You see that the last row is now equal to 0, and we have now 3 independent equations in the first 3 rows of the reduced row echelon form. We can look at this in a slightly more compact way. So let's pass to format short and AB ref. Now it looks like this. We have now 3 independent linear equations, and the fourth row is 0. We now can convert the system into a system with full rank by dropping all the lines, the rows which are 0. So I for now find the rows which are not 0. How do I do this? I sum over the absolute values of the rows, and if this sum is larger than the boundary epsilon, which is about 10 to the minus 16, then we keep the line. So we keep lines, rows 1, 2, 3, and we now take just the rows 1, 2, 3, indices in keep, and store these rows in the same matrix. So we overwrite the matrix with its smaller version. So we now have just the rows which are not 0. Now I extract the matrix on the right-hand side again from this larger matrix. So this is now the system matrix. It's 3 by 4 and the right hand side with 3 entries. And now we can invoke linsolve because the system now has maximal rank. So x3 is this solution, and if we check it, we get rounding errors of the order of 10 to the minus 14, as usual. Now we try to get a general and symbolic solution. Let's invoke linsolve with symbolic arguments. We get a warning, the solution is not unique because the system is rank deficient, but we do get a valid solution x4. Let's check. Let me compute a times x4 minus b. This is exactly 0. So x4 is a valid symbolic solution. Now we do the same trick as before. We look at the null space and we add arbitrary multiples of the basis of the null space. Let's look at the null space. This is dimension 1, so we have only one basis vector. So small n is 1. And we do the same procedure as before. We generate symbolic parameters and we add multiples of these symbolic parameters with the basis vectors of the null space. So this is now XOR, the general solution, has one parameter, T1, and if we check it, we get exactly 0. We can try to recover the original solution. So this was our original solution. This is our general solution. So how can we determine the value of T1 that gives us the original solution x? Well, we solve for the equation x1 equals x all of 1, and this gives the value of the parameter t that will recover the original solution. So if you substitute t0, which is 4, for t1, we get the particular solution we started with. Finally, let's have a look at a rectangular rank deficient system. Here I can show you how to determine whether the system has a solution at all. It can of course be that in the rectangular system there is no solution at all, or in a quadratic rank deficient system there can be no solution at all. Of course, there is always exactly one solution in a quadratic system with full rank. So here I loop over two cases. In the first case, which corresponds to c equals 0, we have an infinite number of solutions. And in the second case, corresponding to c equals 1, we have no solution. And you will see in a minute how we can determine whether there are solutions or not. So let's start this loop. Again, random matrix, capital A. It's of size 2 by 5. And now I add a third row, which is the linear combinations of these two rows. So A is now size 3 by 5, but its rank is only 2. So it's rank deficient. We give an arbitrary solution. It's a vector x. We compute the right-hand side as before. And now we modify B by subtracting C from the bottom entry from the third entry in B. Now, if C equals 0, then we will have solutions. If C equals 1, then there won't be solutions. How can we check that? Well, it's very simple. You just check whether the rank of A is equal to the rank of A and B appended. So rank of A and B. This is the system matrix A, and this is the system matrix with the right-hand side appended to it in the last column. Now, if these two ranks are equal, then the system is solvable. C was 0 in the first iteration in the loop, so these ranks should be equal. We can verify that very easily. Rank is 2 in both cases, so we have solutions. We can try to solve with left division. This will give a warning, rank deficient, but the solution is valid. The right-hand side, A times x2 minus the right-hand side, is of the order of 10 to the minus 15. We can also try with linsolv, gives the same result. Now let's try a symbolic solution with linsolv. This will give again a warning because the solution is not unique. We have an infinite number of solutions. What we get is of course a valid solution, and we can again obtain the general solution by using the basis of the null space. This null space has now dimension 3, so we have to add 3 arbitrary multiples of the basis vectors in the null space. So this gives now the following general solution. You see it in the command window. So it's one particular solution plus T1 times the first basis vector plus T2 times the second basis vector plus T3 times the third basis vector of the null space. And this is indeed the general solution. A times x all minus b is exactly 0. Now let's make the second pass through the loop. C is now 1. We obtain a slightly different matrix. Its rank is again 2, right-hand side. And now we modify the right-hand side by subtracting 1 from the third row in this vector. B is now 0 minus 2019, and now the ranks of the system matrix and the ranks of the extended system matrix, they are different, and this means there is no solution. This works in all cases for quadratic systems, for rectangular systems, for arbitrary rank. So if these ranks are different, then there are no solutions, and we just display system has no solutions, and this is the end of the script.